Welcome to another CHEM271 tutorial. So this tutorial will be all about enzyme kinetics. We will first go into the theory and then we will do a couple practice problems. So first, let's start out with the standard enzyme kinetics graph. So I've labeled it a bit, but just looking at the blue part of it here. So on the x-axis we have S, so this is our substrate concentration, the S with the brackets, right? So substrate, remember, so an enzyme reacts with the substrate goes into the enzyme active site, and then reacts to form a product, okay? So this is the amount of substrate that we have, and then V is the rate of reaction, the rate of catalysis. So the rate at which substrate, given by S, is converted into product, given by P, okay? So I have labeled two variables here. So there are two ways that we can determine sort of how good an enzyme is at converting substrate to product. The first one we can look at from this graph is the vmax. So vmax represents the sort of maximum rate at which the reaction can occur. So essentially, we can see that when we have low substrate concentration, we have low rate, but as we increase the substrate concentration, the rate increases. But it only increases to a certain point. Once we add enough substrate, the reaction rate can't really go up any higher than this. So once we've reached the maximum rate of reaction, that is Vmax, okay? So Vmax is the maximum rate at which substrate can be converted into product. It's also the rate of reaction at which, when all of the enzyme active sites are filled. So essentially when all the active sites of all the enzymes in the reaction mixture are filled, they can't accept any more substrate. They can't go any faster because all of the enzymes have substrate. So essentially, when you have a high enough substrate concentration, the reaction rate can't go any higher because all of the enzymes are busy turning substrate into product. There's no more free enzymes left to pick up more substrate. Okay, so that's why we get a max reaction. So Vmax is defined by these two terms here. The other thing I have listed here is Km. So to understand this, let's first look at the Michaelis-Menten model for enzyme kinetics. So remember, E is enzyme, S is substrate, P is product, okay? So here in the Michaelis-Menten model, enzyme reacts with substrate, and then it converts into the enzyme-substrate complex. So this is the enzyme bound to the substrate at the active site, but the substrate has not yet reacted to turn into product, okay? So this enzyme-substrate complex can form in one direction. The rate constant for that is K1. Or the enzyme-substrate complex can collapse and turn back into the enzyme plus the substrate separately. So that rate is given by K minus 1. So that's sort of the dissociation of the enzyme-substrate complex. The enzyme-substrate complex also has another fate. It can be converted into enzyme plus product. So this is where the substrate reacts to turn into product. So in this case, the rate constant for that is given by K2, okay? So we said K1 is the rate of association of the enzyme and the substrate, so that's the rate of formation of the enzyme-substrate complex. And K minus 1 and K2 are both the rate of dissociation of the enzyme-substrate complex down one of either of the fates of the enzyme-substrate complex. So it can either go in this direction and revert back into the enzyme plus the substrate separately, or the substrate can react to turn into product, leaving us with the enzyme and the product, okay? So the stability of this enzyme-substrate complex can then be defined by this ratio, the rate of dissociation divided by the rate of association. Dissociation is K minus 1 plus K2, so dissociation in this direction or this direction divided by association, so the enzyme and the substrate coming together, so that's given by K1. So K minus 1 plus K2 divided by K1. And that is what we call Km, or the Michaelis constant. So it is sort of the rate at which the enzyme-substrate complex will dissociate divided by the rate at which it will form. Okay, so there are three definitions for this that I have given. So the first definition for Km is the substrate concentration at 1/2 Vmax. So if we look at this graph, right, we can see Km here, and Km is the substrate concentration on the x-axis, where on the y-axis we have reached 1/2 of our maximum rate of reaction. So wherever we get 1/2 Vmax, if we look at the substrate concentration, that's Km. What is the other explanation for this? So it's the amount of substrate needed to fill 1/2 of all of the enzyme active sites. So when we have an amount of substrate equivalent to Km, so substrate concentration equivalent to Km, we know that the rate of reaction will be 1/2 of the maximum rate of reaction. The third definition is the stability of the enzyme substrate complex, right, as we said. So in other words, the binding affinity of the enzyme to the substrate at the active site. So thinking about this, if we have a high Km, that means we have a high rate of dissociation and a low rate of association, okay? So what this means is if we have a higher Km, we have a weaker binding affinity of the enzyme and the substrate. Versus if we have a low Km, we have a high rate of association and a lower rate of dissociation. So the rate of association is greater. That means the enzyme and the substrate have a high binding affinity. So that's good. So basically, a lower Km represents a better enzyme because it means it has a higher rate of association. The enzyme and the substrate are more likely to come together and react. All right? And if there are multiple substrates that an enzyme can react with, the enzymes will react with the substrate with the lowest Km, meaning it will react with the substrate with the highest rate of association relative to the rate of dissociation, okay? Or with the highest binding affinity. So these are the two ways we can think about sort of how well an enzyme can convert substrate into product. If it has a higher vmax, right? So if it has a higher vmax, that means it's able to catalyze a reaction more, that's good. And if it has a lower Km, that is good. So high Vmax is good, low Km is good. Low Km indicates higher stability of the enzyme and the substrate coming together. It also means that you need less substrate to get to Vmax. It means you need less substrate in order to fill up 1/2 of those enzyme active sites and reach Vmax, right? So that is it for now, and then we'll come back and look at some more terms. All right, so now going over some more definitions for enzyme kinetics. So we saw that the dissociation of the enzyme substrate complex into the enzyme plus the product has the rate constant K2. So K2 is also known as kcat, or the turnover number. So it's the rate of catalysis, the rate at which the substrate is converted into product, essentially. Or the enzyme substrate complex is converted into the enzyme plus the product. So how many substrate to product per second? And then to find that, we can use this equation, Vmax equals kcat times the total enzyme concentration. So the total amount of enzyme in the solution divided by the volume of the solution. Another formula we can use is FES. This is the fraction of enzyme substrate complexes. So the fraction of enzymes that are bound to a substrate. There are two ways to find this. You can use V, so the rate divided by the maximum rate, or the specific substrate concentration divided by the substrate concentration plus Km. These are equivalent, okay? So these will both tell you at a specific rate or a specific substrate concentration how many enzymes are bound to substrate. The last one is catalytic efficiency. This is kcat divided by Km. This gives us the specificity of an enzyme for a specific substrate. So essentially, the larger the kcat over Km, the sort of better the enzyme, the faster and the more specific for a substrate. Okay, so this makes sense because if we increase kcat, what do we get? We get faster conversion of substrate to product. And if we decrease Km, that means that you have a smaller amount of substrate needed to reach or to fill 1/2 of all enzyme active sites to reach 1/2 Vmax. Okay, so less substrate needed to fill 1/2 of all enzyme active sites. So higher kcat and lower Km make for a better enzyme. Thus, higher kcat, lower Km give higher catalytic efficiency. Okay, so it indicates that it is a better substrate for the enzyme. And the upper limit of this kcat is actually the diffusion limit of the substrate into the active site. So literally, the enzyme is so quick that as soon as a substrate diffuses into the active site, it immediately reacts. So that's the upper limit, how fast a substrate can even get into the active site. Okay. The next thing I wanted to look at were some graphs. So we've already seen this graph. So we have the rate on the y-axis, substrate concentration on the x-axis. This is the hyperbolic plot. So we have vmax, we have km, we've already discussed this. The equation for this that you do need to memorize is the rate of reaction equals vmax times the substrate concentration divided by km plus the substrate concentration. So multiplied on top, addition on the bottom, okay? And this mirrors the equation for a hyperbolic curve y equals ax divided by b plus x. So it's a standard hyperbolic curve but using the vmax and the km. However, this isn't very helpful because it requires a lot of difficult algebra in order to solve for vmax or km. So there's a much easier way to do this graphically, and it makes the math a lot easier. It's using a Lineweaver-Burk plot. So what this is a double reciprocal plot. So instead of using v and substrate concentration, we're using 1 divided by v and 1 divided by the substrate concentration. So when we do this, what we actually get is a linear plot. We get a straight line when we graph 1 divided by the substrate concentration on the x-axis, 1 divided by the rate on the y-axis, okay? And the equation for this is 1 divided by the rate is equal to km divided by vmax times 1 over the substrate concentration plus 1 over vmax. So you might notice if we compare this to the equation y equals mx plus b, where m is the slope. So the slope here is actually equal to km divided by vmax. The other important thing is that the y-intercept here is equal to 1 divided by vmax. The x-intercept is equal to negative 1 divided by km. So it's actually pretty easy once you get this equation to calculate the x and y intercepts. So using this Lineweaver-Burk plot, it's actually very easy to just calculate vmax and km just given the equation of the straight line. So it makes the math much more simplistic, makes it much easier to calculate the vmax and the km. So the next thing we're going to look at is a practice problem where we will make a Lineweaver-Burk plot and use this equation to solve for vmax and km. All right, for the first practice problem, we are asked to plot this data and find vmax and km. So we're given substrate concentration in micromolar and the rate of reaction V0 in nanomolar per minute. Okay, so essentially the first thing we want to do is get this into a Lineweaver-Burk plot. So to do that, we just do in this column 1 divided by the substrate concentration, and in this column 1 divided by V0. So this will be 1 divided by this column, this will be 1 divided by this column. So in this case, to get this cell, we do 1 divided by 1, which is equal to 1. In this one, we do 1 divided by 3, which is equal to 0.33, so on and so forth. So to fill in this column, we get 0.2, 0.1, 0.033, and 0.02. All right, this column we're doing 1 divided by here, so this is 1 over 11, and this is going to be equal to 0.091, and then this one will be 1 over 25, which is 0.04, and just going down, we get 0.03, 0.022, 0.017, 0.016. All right, so now what we are going to do is plot these in 2 different graphs. So for this first graph is going to be the hyperbolic. Okay, so for the hyperbolic, we're plotting the substrate concentration and the V0. I've already plotted all the points just to save a bit of time, but essentially when we get these plotted and we connect them all, we get a nice hyperbolic plot where we can see we have Vmax somewhere up here, and we have Km maybe around here, roughly. So we can say Km is around 5 maybe, just estimating from this. Vmax is pretty close to 70 from this, but that's just an estimation. So now for the Lineweaver-Burk plot, so this one here is Lineweaver-Burk. All right, so for the Lineweaver-Burk plot, we're plotting 1 over the substrate concentration on the x-axis, 1 divided by the rate on the y-axis. I've already plotted these, and when we connect them this time, we get what is a straight line. So we get a straight line this time. And we get this right here. This is our y-axis. This is going, or the y-intercept, this is going to be 1 over vmax. If we extend this sort of in this direction, we can find here negative 1 over km. All right? So, and remember the slope here is going to be km over vmax. So now we can do some calculations next and sort of figure out what are km, what is vmax, okay? All right, continuing with the same problem, now we're asked to calculate km and vmax. So we are going to use the equation from the Lineweaver-Burk plot in the form y equals mx plus b, and we know that m is equal to km divided by vmax, and b, which is the y-intercept, is equal to 1 over vmax. So we're going to use 2 points to find this. So 2 points in the form 1 over the substrate concentration, comma 1 over the rate of reaction. So this is x comma y, right? Essentially, but using points from the Lineweaver-Burk plot. So I picked 2 points here. We're going to use 1 comma 0.091 and 0.2 comma 0.03. Okay. So the first thing I'm going to do is find the slope, find m. Okay, and to do this, y2 minus y1 divided by x2 minus x1. So this will be 2, and this one will be 1. Okay, so we get 1, we get 0.091 minus 0.03, so the y is over the x. 1 minus 0.2. And I'm just leaving units out of this just to make it a little easier and a little faster. This gives us a slope of 0.07625. This is just an approximation, by the way. If you put all these plots in Excel and use a linear regression model, you'll get a much more accurate answer, but since you can't use Excel on a test, and if you come across this kind of problem, this is how you would do it by hand. So, right, so now we have the slope. Okay, so the next thing to do, we have y equals mx plus b. What we want to do is solve for b. So b is equal to y minus mx. Okay, so in this case, we are going to use this 1 comma 0.091. So we know b is equal to our y value, 0.091, minus m, 0.07625, times our x value, which is 1. So we really just get 0.091 minus 0.07625. And with this, we get a value of b of 0.01475. All right, so now we can calculate vmax. So vmax, we're going to use this equation. So we multiply it by vmax, divide by b. So vmax is equal to 1 over b, which is equal to 1 divided by 0.01475. And this gets us 67.8, and then adding back in the units at the end, nanomolar per minute. So this is actually pretty good. So we said on the last part, it was around 70. That's pretty close to what we saw from the graph, all right? So now using this to find km, we just multiply both sides by vmax. So we get km is equal to vmax times m, which is equal to 67.8 nanomolar per minute times our slope. I'm actually just going to get rid of the units just to make it a little easier. We'll add them in at the end. So that, and then times our slope, which is 0.07625, and what we get is 5.17 micromolar, which is also about what we predicted. So this is our Vmax, and this is our Km. Not bad, not bad. Lines pretty well with our prediction. On to the next part. Find kcat, given the enzyme has a mass of 29.6 kilodaltons, and our solution that the enzyme is in is 10 ml, and it contains 10 to the minus 9 grams of protein. So the first thing we do here is we have to know that 1 Dalton is equal to 1 gram per mole. So 1 kilodalton is equal to 1,000 grams per mole. So this is just our conversion factor that we're going to be using. So we have a mass of 29.6 kilodaltons. So kilodaltons. And so we have 1,000 gram per mole in a kilodalton, right? So the kilodaltons cancel, and this gets us a molecular weight of 29,600 grams per mole. We'll switch to a different marker. Okay, so now that we have that, we can then convert this amount of grams into moles. So 10 to the minus 9, ooh, much better. Grams times in a mole, we have, so we would divide by 29,600 grams, the grams cancel, and what we are left with is 3.38 times 10 to the minus 14 moles of protein. Okay, and we know our volume, 10 ml, this is 0.01 liter. We know that just from a simple conversion. Okay, so we can then find 3.38 times 10 to the minus 14 mole divided by 0.01 liter is equal to 3.38 times 10 to the minus 12 moles per liter. All right, so now we can find vmax. So remember, so remember the equation is kcat is equal to vmax times the concentration of enzyme total. Okay? So in order for this equation to work, we have to get the units of vmax to be the same. So we need to get the units of vmax into moles per second. Okay, so in order for this to cancel out and give us the correct units for kcat. So vmax is equal to 67.8. We're in nanomolar per minute, and we need to get to molar per second. Okay, so to can get out of nanomolar and get into molar, we divide by 10 to the 9th. So there are 10 to the 9th nanomolars in a molar. And then we can get rid of the minute. A minute we know is 60 seconds, right? So the minutes cancel, nanomolars cancel, and we will get moles per second. So here we get 1.13 times 10 to the minus 9 moles per second. No, it still shows. Okay, I'm gonna just erase this and rewrite it. So kcat is equal to vmax. This is wrong up here. Vmax divided by E total. So remember the equation back from the last bit ago is Vmax equals kcat times E total. So in order to isolate for kcat, we get Vmax divided by E total. Sorry about that. So Vmax over E total, which is equal to 1.13 times 10 to the minus 9 molar per second divided by the total amount of enzyme, which is 3.38 times 10 to the minus 12 molar, and we get that kcat finally is equal to 334 seconds to the minus 1. So that's our rate constant. Okay, so we are converting these substrate to product at this rate, 334 compounds per second. Or just unitless there. Okay, so that's just a rate constant. It doesn't have any sort of unit for moles or anything. The last part that I wanted to add was find the catalytic efficiency, which is kcat over km. So this is pretty easy since we have km in micromoles, so we need to convert that. So we can find that km is equal to 5.17 times 10 to the minus 6 molar. Okay, so that's just getting it in the same unit. And then kcat over km is going to be equal to 334 seconds to the minus 1 over 5.17 times 10 to the minus 6 molar, and we get a kcat of 6.46 times 10 to the 7 seconds to the minus 1 molar to the minus 1, which is fairly good. All right, so that's quite a lot for this problem, but just to summarize what we did, we found Km, we found vmax, we found kcat, and we found our catalytic efficiency. All right, so all that just from the data from the graph, and we did it all manually. So you can also do this in Excel, it's probably easier, but we did it by hand. So, okay, next question. All right, the next question is much shorter than the last one. Find Vmax if V0 equals 1 micromole per minute and the substrate concentration is equal to 10 km. So we're using just the hyperbolic equation here, nothing crazy. Okay, so what we're going to do is we're just going to substitute in these variables first. So V0 equals 1 micromole per minute. This is just a rate, this isn't the maximum rate, it's just the current rate of reaction at the substrate concentration. Equals Vmax. Okay, and then we're multiplying this by 10 km over km plus 10 km. Okay, so we can simplify this further. So 10 km times Vmax equals, so 1 km plus 10 km is 11 km. So these cancel. So we get 1 micromole per minute equals 10 over 11 Vmax. So then we can find Vmax is equal to just 11 over 10, so multiplied by the reciprocal, times 1 micromole per minute, which is equal to 1.1 micromoles per minute. All right, so fairly straightforward problem. All we did was just substitute in the variables and solve, but this is a pretty common type of problem that you could expect to see on an exam. So that'll be it for this video. The next video, we'll be looking at enzyme inhibition. All right, thank you for watching.